So just kind of reviewing some basics of our exponent rules. And you can write this on your paper if you have some space at the top, whatever. Just to kind of go over some simple stuff. If I have x squared times x to the 7th, what kind of problem is this? Multiplication. And when I multiply, what do I do with my exponents? And I get x to the... Yes. Okay, just some basic division. If I have x to the 7th over x to the 4th, when you divide, what do you do with your exponents? Subtract, and you get x to the 3rd. Okay, and then kind of getting a little more complicated. If I had, well, actually, we'll make an easy one. So let's do x to the 2nd, x to the 4th to the 5th power. X to the 2nd times x to the 4th to the 5th power. What is that? Like, how do we simplify that one? Oh, sorry. Let me change that. Yes, you could, but let me change that to a y because that's what I meant to do. And that would make way more sense on this problem. Okay, there you go. What would you do now? Yeah, you multiply the exponent in there. So that would be 5 times 2 would give me x to the 10th. And then 5 times 4 would give me y to the 20th. Okay. All right. And then just some other things, and this is the part that I think gave the most trouble yesterday, is introducing this idea of negative exponents. Yeah, so some people were good with just like, this is what you do. Some people were like, but why do you do that? So I wanted to introduce this, just go back over this idea of negative exponents and what that means. So if we have 12x to the 5th, y to the negative 4th over 3x squared, y to the 7th. So the thing we talked about yesterday was if we have negative exponents, we can move them from wherever they are to the opposite place in the fraction. So currently this y to the negative 4th is on top. So therefore to make it positive, we can move it to the bottom, to the denominator. And the question that's been coming up yesterday and today both is why? Why does that work? So I want to explain that because I think some of you need to know why it works in order to understand that it works. And that's fine because sometimes your minds are wired that way. Some of you are just like, you say it's true, okay, I believe you, and I can just do that process. So just different people work different ways, and that's fine. So think about, this is a division problem ultimately because I have stuff in a fraction. And when we divide, what do we do with our exponents? We subtract. And we always want to subtract the way that makes sense. Like we always want to do the biggest exponent minus the smallest exponent. Because otherwise you end up with negative exponents, and we don't want negative exponents. So that's ineffective. So for the x's, for example, we would do 5 minus 2. We would do the top minus the bottom. What is 5 minus 2? 3. And I would end up with 3 x's on top. Because when we started subtracting, we started from the numerator. Therefore, my answer would still be in the numerator. Okay, now looking at your y's, what's bigger, negative 4 or 7? 7. So mathematically, we are going to do 7 minus negative 4. Well, I'm going to write that because I need you to think about what that means. If I have 7 minus negative 4, that's really what? 7 plus 4, which is 11. So really, I'm going to have y to the 11th. Where are those 11 y's going to be? And y on the bottom. That's where you started from, and like the bigger number was on bottom. So I end up with y to the 11th. Okay, talk to me about my numbers. 12 over 3. 4, and that's going to go where? Yeah. So if I had, from the very beginning, rewritten this problem as 12, because some of you are saying, oh, I just need to move it around. If I had written this as y to the positive 4th in the denominator, what do you do with the 7 and the 4 that are both in the denominator? You add them, which is what we ended up doing here, was we ended up adding 7 and 4 anyways. So either way it works, whatever makes the most sense to you. Because some people, like a kid in first period was like, oh, I get that way better than I get just flipping it. I was like, okay, I don't care, just do the math. As long as you do the math and you do the math right, and what you're doing isn't like some trick that just happened to work one time, then I don't really care how you get the answer. So as long as, again, you are the one doing said math. Yesterday when we stopped at like question 8, I think. Did we talk about 8? No. Okay. Okay, so we didn't talk about 8. But so we have the cube root of y. That's y to the first. Okay, I want to just to talk about this for a second and just to kind of introduce or review what we did yesterday. Okay, so I can rewrite this as y to the 1/3. I just need y'all to remember that there's a connection here, that this 3 becomes your denominator and this 1 becomes your numerator. Is there anything else that we can do to that problem? No, because if we have a cube root, that means we're looking for groups of 3. Well, I only have one y on the inside. There's no way to get a group of 3 y's out of that if there's only one there. So really, this problem is as simple as it goes. So there's nothing else to do to that one. Look at problem 9. We have, what root is this one asking for? Square root. Anytime it doesn't have a number, remember there is a 2 there. It is implied. So I have the square root of a to the 3rd, which means that I'm looking for groups of 2's. So how many a's do I have on the inside of my problem? 3. And I'm looking for groups of 2. So how many groups of 2's am I going to have? 1. And I'm going to have how many left on the inside that don't group up? 1. So my answer becomes a square root of a. That would be my answer to the problem. It would be a square root of a. And you can write the 2 as the square root. You cannot write the 2 as the square root. It's kind of the same concept of writing a coefficient of 1. Having a 1 in front of a variable doesn't make the problem any more right or any more wrong. It's the same idea with having a square, like the 2 as the root there. It's implied. Okay, so look at the back. Let's start with 17. So the problem is that you just kind of get all these problems thrown at you, and there's no like, hey, you do this first. You just kind of have to look at it and say, okay, what can I do? And let me try and do that and see what I end up with. So like problem 17, you have x to the 4th, y to the 6th to the 1/2 power. What could you do? What do you mean you write it out how? Okay. So we could write square root of x to the 4th, y to the 6th. What did you say, Riley? Because you said something different. Okay, so you could distribute the exponent. Hey, guess what? They both work. Doesn't matter. We're going to do both because I think it's important for you to see both because they both literally produce the same answer. So I'm going to start on the left side. I drew a line so I could work it out 2 different ways. First time I write, I'm going to write the square root of x to the 4th, y to the 6th. And the reason I know it's a square root is because my denominator was a 2. So because it was x to the 1 or something to the 1/2 power, that meant square root. Well, if I'm square rooting it, I'm looking for groups of 2's. So if I have 4 x's, how many groups of 2's do I have? 2. Are there any left over? Nope. So I'll have x squared on the outside. And then I have y to the 6th, and I'm square rooting that. So there's 6 y's. How many groups of 2 would that be? 3. So I'll have y to the 3rd. Okay, so then the other thought was, oh, hey, I could distribute that 1/2 in. That's what Riley had told us she would do. So, okay, what's 1/2 times 4? What is 1/2 times 6? Did we get the same answer either way? They both work. And one is not necessarily more right than the other. It's just whichever you see first. And that depends on you. And I can't tell you, you do this. Like, you have to do what you see and you start working that out because eventually something will happen. Look at problem 18. What kind of problem is this? We've got not square roots. What roots are we going to have? We have 5th roots in there. Okay. There's a division problem, though, isn't it, ultimately? And there's some multiplication in there, isn't there? Okay. So what could I do? What are some things I could do here? I could combine my terms. I could go ahead and simplify this a little bit. So what could I do with the 3 and the 2/5 on top? Why do you add them? They're being multiplied. So 3 plus 2 over 5. Do not tell me 3 and 2/5. I know that. Give it to me in an improper fraction. 17 over 5. And don't tell me 3.4 either. That's even worse. Can do nothing with that. Okay, yeah, you cannot have decimals in your exponents. No, not even a thing. So if you're not sure where we got that 3, if I need to add 3 plus 2 over 5, so I've got to get common denominators. So I got to multiply 3 over 1 by 5 over 5 so I can then add them together. Okay. Or you can use calculator. 3 plus 2 over 5. Math, enter, enter. It will also give you the fractional form of that exponent, which is what we need. Over x to the 1/5. Now it's a division problem. When we divide, what do we do with our exponents? Subtract. So what is 17 over 5 minus 1 over 5? Yeah. Yeah, and if I were to give a rule of thumb, like to say, hey, this is what I would do, I always simplify everything before I start dealing with, like, radicals. Like, I always want to simplify everything before I ever start, like, dealing with any radicals on stuff. So, 16 over 5. If I divided it, it would be 3 1/5. I'm going to write this out as the 5th root of x to the 16th. Just so we can see it, because some people need to see it like that. And I'm even going to go even further, and because some of you are still like, what are you talking about when you talk about grouping? Okay, so I have 16 x's here. And because I'm looking for the 5th root, I need to find groups of 5. So 1, 2, 3, 4, 5. That is one group of 5. That means I can take it outside. It can go in front. And then I can repeat that. 1, 2, 3, 4, 5. This is what we're doing when we are dividing. There's another group of 5. 1, 2, 3, 4, 5. There's another group of 5. So how many groups of 5 did we end up with? 3. And that's the same thing. If you divide 16 by 5, it goes in 3 times. And how many x's are left over and lonely inside the house? 1. Sorry, that should be x to the 3rd. And yes, there would be that 5th root there. Sorry. There we go. So our answer is x cubed to the 5th power. And again, we would have gotten the same thing if we had looked at our original problem and we said, okay, what is 16 divided by 5? Well, 5 goes into 16 3 times. So that means there's 3 x's outside and there's 1 x that's left over because there's a remainder of 1. So it works the same way. This is the long way of doing it where we expand it out. But for some of you, that's the way that makes sense because you can visually see what you're doing. And some of you need to see that. That's okay. I don't care. Okay? I don't care if you divide it. I don't care if you write it all out. The problem with writing it all out, it's going to take you a little bit longer. But it's not the end of the world. Okay. Look at problem, 19. I love 19. 19 is a fun problem. It doesn't look fun? Why not? Like multiple square roots? Okay, what if there was one square root?
I don't like the bottom.
Okay, does that look better?
You know how to fix it.
Do what?
You know how to fix it.
You know how to fix it. What do you do to fix it?
You look to the top. It's a C over
Yeah.
Okay, that would move.
when you combine those two C's.
Okay, so I can do some simplifying here. If I combine them, I'm left with C to the 7th. And what about my D's? What do I end up with?
4. No, you subtract 9.
Yeah.
You subtract and you get D to the 9th. Because I have some D's on top, some D's on bottom, and I get D to the 9th here. So I combined my C's, I added the exponents, and got C to the 7th. I subtracted my D's because one was on top, one was on bottom. And can I simplify this problem even further?
Yeah.
Yeah, because I'm looking for the square root, which means I'm looking for numbers I can group into groups of 2. So if I have 7 C's, how many groups of 2 can I come up with? 3. So that'll be C to the 3rd on the outside. And what's left over on the inside? Okay, I have 1 C left over. I'm just starting with those. Okay. And then I have D to the 9th. So how many groups of 2 can I come up with? I have 9 D's. 4. Nope. D to the 4th. And then what would be left over? D on the inside. So that would be your final answer. Not terrible.
These are not hard.
They're not hard. There's just no, like, they're just kind of all different. Like, each problem's like its own problem, and you got to figure out what to do with said problem. And that's where things get complicated, is there's no, like, step 1, you do this. Step 2, you do this. Step 3, you do this. And sometimes what you get as your answer can't actually even be your answer. Look at problem 16. Oh, 16's good. It's okay. All right, what do I do?
Switch the negative 9 to
Okay, switch some stuff around. So my x to the negative 9th is going to move to the top and become x to the positive 9th. Okay, what else is going to happen? My y to the negative 3rd is going to go to the bottom. It's going to become positive. Then I can combine my x's. I'm going to extend my root symbol out because that really annoys me when, like, I have a number that's like underneath the square root, but it's not actually like underneath the square root when I write it. So, okay, I heard I can combine stuff. So if I were to combine stuff, what would I actually end up with? The 5th root of what? Y10. Okay. That's not terrible. Can I do anything else with that? Okay. I can group them. So how many groups of x's am I going to end up with? 2 groups of x's, and how many x's are left over? 3. And how many groups of y are there? 2. Are there any y's left over? No. That worked out well. Because why not? Division is division. Because let me give you some numbers because that would help solidify this. 5 over 2 times 4 is the same thing as 5 times 4 over 2. So it doesn't matter if it's under like the whole thing or just part of it. If it's like everything in the numerator is being multiplied, it's the same thing. So that is why I wrote that as x squared the times the 5th root of x to the 3rd all over y squared. Valid question. Okay. 15. 4th root of x squared. Can I group that and simplify it? So how many x's are on the inside technically?
1.
But I'm squaring it, so really there's 2. And I'm supposed to put it into groups of 4. Can I do that? Okay. Let's rewrite this using a fractional exponent. So if I have x, the 4th root of x squared, I can really write that as x to the 1/2 power. Wait, where'd you get 1/2 power? Yes, because it's really x to the 2 over 4. I could rewrite it like that. And 2 over 4 is actually 1/2. So really, this problem is actually what? The square root of x. So I can reduce those as well. That works out kind of nice. Not terrible. Could you do the same thing on 14? You can't reduce it because they're both prime numbers. So, but if they had some common factor, then yes, you could. You could apply that same principle. It just 14 didn't work out that way because of the numbers that we had there. Yeah, so it'd be that. I know. Let me get through 12. Okay, 12. I have the cube root of x to the 6th. Why? Another way around, but yes. This would end up being x to the 2nd power. Because how many, if you have, like you're looking for, you have 6 x's on the inside, you're looking for groups of 3. How many groups of 3 can you come up with? 2. And you could also think of this as rewriting it as x to the 6 over 3 power, and 6 divided by 3 is 2. So I end up with x squared. So looking at problem number 10, we have the cube root of negative x to the 5th power. And remember, I can take the cube root of negative numbers. That's totally fine. And even if it was a square root of negative x, that is okay. I need you to realize that this is an acceptable problem that can give you a real answer. Like, this is going to give you something. This is not. The square root of negative 4 is 2i. That is going to give you an imaginary number. But the square root of negative x isn't necessarily going to give you something imaginary. And the reason is because we don't know what x is. X could be any number in the world. And in particular, if x was some negative number, if x was less than 0, like let's say x was negative 4, and again, I'm just making this up, then really I have the square root of negative 4, and when I have a negative, that's really a positive, so really this is the square root of 4, which is 2. So don't let this part, this negative sign in here, freak you out. Like, you can still work with it, it's just saying there's a negative sign somewhere. So I have, looking at this, I have the cube root of the square, or cube root of negative x all to the 5th power. So essentially what's happening is I have the cube root of, and I have negative x 5 times. Oops. And I'm looking for groups of 3. So I have 3 x's here, so that means I have a negative x on the outside, and then I'm left with 2 negative x's on the inside, and if I multiply that back out, negative x times negative x is positive x squared. So my answer ends up being negative x times the cube root of x squared. Okay, problem 11. I have the cube root of 2xy to the 5th. This one's not terrible, it just has a fraction in there, but it's the whole problem itself isn't awful. So if we look at that for what it is, then that means I'm going to have 5 of these 2x over y's on the inside, and I'm looking for groups of 3, so I'm going to come up with one group of 3, and then I'm left with 2x over y squared in the denominator, or in the inside the radical symbol. Now, unfortunately, I am not done with this problem, and the reason that I am not done with this problem is because I cannot leave square roots in the denominator. I must rationalize them. That should say them, not the. I must rationalize them. And we have done this before. It's been a while, but we have done this. So we're going to talk about how we rationalize. In order for us to do that, I need to rewrite this problem so you can see it a little bit better. So I'm going to write what I have so far. Actually, just so you know, I'm not going to rewrite this part. This part is fine for right now. I'm only focusing on this because this is where my problem is. And the problem is that I have this y in the denominator and I can't have that. So I'm going to focus on just the cube root of 2x over y squared. So I'm going to rewrite this as two things. The cube root of 2x squared, quantity squared, over the cube root of y squared. And I'm writing it as these two so that you can see where exactly the problem lies. So notice I have this cube root in the denominator. That is my problem. And I'm going to even go a little bit further, and I'm actually going to write this as the cube root of 2x to the 2nd power over, actually let me make that a little bit better, 2x to the 2nd power, that's really 4x squared. Because if I take 2 squared, that's 4, and 2x squared is still x squared. So really it's 3, the cube root of 4x squared over, I'm going to write this as y to the 2/3 power. I'm going to write that as y to the 2/3 power. And when we need to rationalize this, that means I need to multiply the numerator and the denominator by a helpful form of 1, by something that will take care of this cube root, by something that will get rid of this denominator of 3 here. In order to do this, you have to remember that when you multiply two things together, you really add their exponents. So I need something that I can add y to some power, and it will give me a whole number. That's what I'm looking for, is I'm looking for something that will give me a whole number. And if I have 2/3 and I need to get a whole number, then I need to add 1/3 to that. Because 2/3 plus 1/3 is 1, which means I need to do the same thing in the numerator. So now, this gives me something a little bit different. It gives me the cube root, I still have on top, the cube root of 4x squared times, and I'm going to rewrite this as the cube root of y, and you'll see why in a second, over, and all of this in the denominator, every bit of this in the denominator is actually going to give me just y. And that's what I want, because now I don't have y in a radical symbol, I just have a variable. And I'm good with that. We can have variables in the denominator. We cannot have radical symbols in the denominator. So now let's fix this numerator a little bit, because this looks kind of ugly, because I have the cube root of something, and then I have another cube root of something. And hey, guess what? If I'm multiplying, I can just put those cube roots together. So really, that's the cube root of 4x squared y. And then all over just y, not y in the square root symbol. And then don't forget, originally in the problem, we had 2x over y here. So remember, this 2x over y comes from this 2x over y up here. So I just ignored it for a little bit because I didn't need to do anything with it. Well, I can actually kind of multiply that out a little bit, not a whole lot, but I can do something with it to make it look a little bit better. So really this becomes 2x, because I'm multiplying 2x times the cube root of 4x squared y divided by y squared. And the reason it's y squared is because I had y in the denominator and I had another y in the denominator, and y times y is y squared. Now, some of you probably wanted to be like, oh look, up here, I have a y on top and a y on bottom, so I can just go ahead and cancel those y's out. No, you cannot do that. No, 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 you cannot do that. The reason you cannot do that is because this y, it's stuck inside a cube root symbol, and this y, it's not stuck inside a cube root symbol. So we cannot cancel those out. We can only cancel them out if they have the same variables with the same exponents. They don't have the same exponents, so we cannot cancel those out. So my final answer to this problem is this 2x times the cube root of 4x squared y over y squared. I'm going to do a couple more problems where we have to rationalize, don't worry, where we have to go through this whole process. So I'm going to do some from the homework. Look at problem 13. I have the cube root of y to the 5th power. Well, if I divide that, 5 divided by 3 is going to give me 1. So I'm going to have y to the 1st on the outside. And then cube root of, I'm going to have 2 left over on the inside. And again, that happens because 5 divided by 3 equals 1 with a remainder of 2. So the 1 goes outside and the 2 goes inside. The remainder goes inside. That's where those came from. Last problem I think on the notes is problem 20. I'm not going to do 14 because 14 you cannot do anything else to it. So problem 20, and there were some questions about this that I got asked periodically throughout the day, and I had people messaging me on Remind over the weekend. So I wanted to address this question. I'm going to do it 3 different ways because some of you are going to be like, what did you do? And others of you are going to be like, oh, good. So I'm going to kind of address this problem 3 different ways, and I'm going to talk about how they really all end up being the exact same thing. So the first way I'm going to do this is I'm going to do this the easiest way and the way that I would like for you to do the problem, but if it doesn't make sense to you, then don't do it this way. So you all know that if you have a negative exponent, then that means that you've got to do some flipping around. You've got to do some moving. Some things that are in the numerator go to the denominator, denominators go to the numerator, all of that. So if I have 4 over 7, x to the 3rd to the negative 2nd power, I'm going to fix the inside part first. And I'm going to write this as, and I'm going to tell you why, I'm going to write this as 4x to the third over 7 all to the negative second power. The reason I can do that is because here, this x to the third is not in a fraction. So to get anything into a fraction, I can put it over 1. And then when I put it over 1, I multiply my numerators, and that's where I get my 4x cubed from. And I multiply my denominators. 7 times 1 is 7. That's where my denominator comes from. So now I can deal with this whole negative exponent thing. So I have this negative 2 that's causing all my problems. And what we learned last week was that if I have a negative exponent on top, I can move it to the bottom. And if I have a negative exponent on bottom, I can move it to the top. Well, let me kind of make that a little bit more simple. If this whole thing has a negative exponent, then that means that that whole thing can get flipped over. So really my problem is 7 over 4x cubed to the second power. That's it. Well, now I can actually square that. Remember, exponents outside get distributed to all the exponents inside. Let me make sure everything has an exponent on the inside. So 2 times 1 is going to give me 7 squared. 2 times 1 is going to give me 4 squared. 2 times 3 is going to give me x to the 6th. And just doing some basic math, I end up with 49 over 16x to the 6th. That's the answer that we're going to come up with. And we're going to find this answer by doing 3 different things. Because some of you are like, what did you do? Why did you do that? Okay, no. So I'm going to do this problem a different way. Okay? So the second way that I'm going to do this problem is I'm going to treat this whole thing, 4 over 7 x to the third to the second, negative second power, as a fraction. Because I can make anything into a fraction by putting it over 1. And we know that if I have a negative exponent, that means that I've got to move whatever, if it's on the top and it's a negative exponent, I have to move the entire thing to the denominator. So I'm going to move 4 over 7 x to the third to the positive second power to the denominator. So now it's gone. Now, that doesn't mean my numerator disappears. That means I need to put something there to occupy the space that's no longer filled. So I'm going to put a 1 up there. So really I have 1 in the numerator. So let me rewrite this problem just so it looks a little better. So now I have 1 over 4 over 7 x to the third to the second power. Okay, so let's distribute that exponent in because we still got to do that. So everything needs an exponent. 2 times 1 is 2, so that's 4 squared. Oops, sorry. Let's try this again. That's 1 over 4 squared. 2 times 1 is 2, so 7 squared, times 2 times 3 is x to the 6th. And that really gives me, because I just need to make that look a little bit better, I get 1 over 16 over 49 times x to the 6th. Well, we've done a lot of stuff with fractions lately, and we know that dividing by a fraction is the same thing as multiplying by the reciprocal. So really this is the same thing as saying times 49 over 16. And then I can multiply my numerators, 49. I can multiply my denominators, 16x to the 6th. That's my answer. And lo and behold, it's the exact same answer that I came up with over here on this first side. Some of you are still like, nope, 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 not anymore, not anymore. So let's try it a third way. Because they all work, I promise. So the third option is we have 4 over 7 x to the negative third. Sorry, x to the positive third. My bad. To the negative second power. So I'm going to go ahead, I'm just going to distribute that exponent in now. Give everything an exponent and go ahead and multiply it in. Negative 2 times 1 gives me 4 to the negative second. Negative 2 times 1 gives me 7 to the negative second. Negative 2 times 3 gives me x to the negative 6th. So I got to move some stuff around because if I got negative exponents, I can't have that. So that 4 to the negative second is going to move to the denominator and become 4 to the positive second. 7 to the negative second is going to move to the numerator and become 7 to the positive second. This x to the negative 6th is in the numerator because there's really a 1 here in the denominator because we can make anything into a fraction by putting a 1 underneath it. So that means that I can move this x to the negative 6th to my denominator and it becomes x to the positive 6th. Well, simplifying that, we get 49 over 16. And then I have this x to the 6 in the denominator, so I'm really just going to make that one giant fraction because it's a multiplication problem. So my answer is 49 over 16x to the 6th. And again, it's the same answer I got the other 2 times I did it. So it doesn't matter which way you do the problem, it just depends on which way the problem makes sense to you. Okay, so I'm going to do problem 34 from your homework. So we have the square root of 48x cubed y to the 4th over the cube root of 8xy to the 5th. It would be super convenient if our roots were the same, like they both had a 3 there, but they don't. This one has a 2, so I can't just make them into one giant problem. I have to treat them separately. So let's start with the numerator. So I have 48x cubed y to the 4th. The variables are pretty easy to work with. So if I do 3 divided by 2, I'm going to get 1x on the outside and then 1x on the inside. And if I do 4 divided by 2, I'm going to end up with 2 y's on the outside. And then 48, I need to think about 48 as all of the possible all of its factors, and I need to figure out what the perfect squares are. So 48 is 1 times 48, 2 times 24, 3 times 16, 4 times 12, and 6 times 8. And if I look at these numbers, I have several perfect squares here. 4 is a perfect square, 16 is a perfect square, 1 is a perfect square, and of those, 16 is the biggest. So I can think of this as the square root. Instead of the square root of 48, I can think of it as the square root of 3 times the square root of 16. The square root of 3 doesn't exist, not as a whole number, so we're going to leave it on the inside. The square root of 16 is 4. So this is now my numerator of my problem. 4xy squared times the square root of 3x. That's my entire numerator. So now I'm going to work with the denominator. So my denominator was the cube root of 8xy to the 5th. Well, it's not terrible. The cube root of 8 is 2. Because 8 is really 2 times 2 times 2, so there's 3 2's there. I can take the cube root of 8, so that's going to, or of x, that's going to stay on the inside. If I think about the cube root of y to the 5th, then that means I'm going to have 2. If I divide 5 by 3, I get 1, so I'm going to have 1 y outside. My remainder is 2, so 2 y's on the inside. So this is now my problem, which is, again, not horrible looking, but not terrible. And I can simplify that a little bit in a couple ways. First of all, I can go ahead and these numbers here, 4 and 2, I can divide those because 4 divided by 2 is really just 2. So my problem is actually 2xy squared times the square root of 3x over y times the cube root of xy squared. So I need to rationalize this, and that means I need to get rid of this whole idea of this cube root xy squared in the denominator because I can't have that. So I'm going to focus on just this part for a minute, this cube root of xy squared, because it's in the denominator, and that is where my problem lies. So I'm going to write that as instead x to the 1/3 power times y to the 2/3 power. And the reason I can do that is because, remember, I have, if this is my radical, or this is my root, I'm sorry, it becomes my denominators. So this is really x to the 1/3, y to the 2/3 power. So when we talked about rationalizing earlier, that meant that we had to multiply by something to get rid of whatever it was in the denominator that was causing the problems. So I've got to multiply by x to some power, and I've got to multiply by y to some power, and I've got to do that in both the numerator and the denominator. so that I can keep it equal. Keep it as really just 1 is all I'm doing is multiplying by 1. But what has to be true is that when I add this 1/3 and whatever else I'm going to add to it, it has to give me a whole number. So that's going to have to be 2/3 because 1/3 plus 2/3 is going to give me a whole number of 1. Okay, so that's going to multiply by 2/3 on the top. X to the 2/3. And then same with the denominator of y to the 2/3. I've got to multiply by something here that when I add them together gives me a whole number. So that's going to be 1/3. Just got to do that on both top and bottom. So now my problem says 2xy squared times the square root of 3x times, let me write that a little bit differently because you're going to see something really cool. I'm going to keep 3 to the 1/2, and then I'm going to write this as x to the 1/2, and I also have x to the 2/3 on top, and I have y to the 1/3 on top. And then on the bottom, I have my y that was already there, and then conveniently x to the 1/3 and x to the 2/3 just gives me x, and then my y to the 2/3 and y to the 1/3 gives me a y. So it doesn't look much better, but it's getting there. We're going to make it look better, so we're working on it. All right, so now I got 2xy squared times 3 to the 1/2, all in the numerator. And then I got all this other stuff over here. So notice that I have x to the 1/2 and x to the 2/3. They both have x. That means I can add them together. In order to do that, got to get a common denominator. Whoops. Got to get a common denominator, so I'm going to have to figure out what the common denominator is going to be, which isn't the end of the world. So we just got to do some math here to decide that. So I'm going to figure out just focus on these for a second, and I know my common denominator is going to be 6, so this is 3/6, and this is 4/6. So if I add them together, then I now have actually x to the 7/6, y to the 1/3, and then fixing the bottom a little bit, I really have x y squared because I had an x already and I had a y times a y. Hey, look, that looks a little bit better because notice you have an x on top and bottom and y squared on top and bottom. They're going to cancel. Okay, so we're getting better, getting better. And then I'm seeing that I have all these exponents here, and I don't like that. So what I'm going to do, and you're going to be like, why are you doing this? Just trust me. Trust me that I know what I am doing. I'm going to write this 1/2 as 3 to the 6th, because it is 3 to the 6th. And I'm going to write this 1/3 as 2 to the 6th. And you're like, why did you do that? The reason I did that is because now all of my denominators are 6, and I can put this in one root symbol. So I still have 2 on the outside, but now I have the 6th root of 3 to the 3rd power, x to the 7th power, and y to the 2nd power. Okay, we're getting better. And we're almost done. I know you're like, this problem has taken forever. I acknowledge this. I'm not going to say it's been a short problem, but we are almost done. And there's a little bit more we can do, not a whole lot. The first thing we can do is I can go ahead and figure out what the cube root or 3 to the 3rd power is. That's easy. That's 27. So really this is 27. And then I have this x to the 7th. I can simplify that because if I do 7 and I divide it by 6, I get 1 left. I have 1, and then I have 1 left over, so that means I'm going to have an x outside and an x inside. And then y squared, because can't really do anything with that. So look, that is my final answer. I know that problem that started off so horrible looking, turned out to be something so decent looking, but I also know there was a lot of work that went into getting that. So hopefully that reviewed the idea of rationalizing, and that went over what to do on problems where the exponents are different. That's going to apply to 35, but 35 is just easier because notice 35 just has x's in it. So that's going to be a whole lot easier to work with. And that's only 2 problems, I think, that where you had different roots. And honestly, for 35, this one's actually way easier because I would write this as x to the 4 over 9 over x to the 2 over 6. And then I would subtract them, which we need a common denominator, but I can reduce that. So this x to the 2/6 is actually x to the 1/3. That is actually x to the 1/3, because 2 over 6 reduces to 1 over 3. And then I can get a common denominator of 9, and then I can subtract these. So this is really 3 over 9. And if I have x to the 4 over 9 divided by x to the 3 over 9, I can subtract those, and I get x to the 1/9, which is really just the 9th root of x. So that would be my final answer.